This is Mr. Holsey with H Squared Sufficiently Understood Science, and today we're going to be looking at the timeline of the universe. So this is going to be our map right here, and we're going to go all the way from the Big Bang to the end of present day. And so all the numbers I'm giving you today are going to be based on time after the Big Bang. So as far as we can see back is going to be about right here. Okay, so we can see all of this. So we know quite a lot about this. But thanks to things like the CERN collider, the Large Hadron Collider, we're able to recreate conditions here. And so we can kind of understand how the early universe would have worked. So we're going to start down here at the Big Bang. So in this beginning, the universe begins some 13.7 billion years ago with an event known as the Big Bang. Both time and space are created in this event. So one thing we need to understand is this term Big Bang. It was not a bang, okay? More like big, and let me pick a way different color than that. Big expansion. Okay, so this is a huge expansion, all space, all time, going out at once. People often ask me, okay, so what was it expanding into? Well, technically it wasn't expanding into anything because there's nothing outside of the universe. By definition, the universe is everything. So at 10 to the negative 43 seconds. And so the cosmos goes through super fast inflation, expanding from the size of an atom to the size of a grapefruit in a tiny fraction of a second. Now, while a grapefruit doesn't sound all that impressive, that is massive. It's just insane, the growth. And to give you an idea of how very little seconds there are going on here, we're going to use scientific notation. Okay, so keep in mind this doesn't mean that I'm adding 43 zeros or anything like that. It means I'm moving the decimal point 43 places, and because it's a negative number, I'm going to be moving it in that direction, so to the left. All right, so I'm going to write this number out really quick. I'm going to put 10 right here, have my decimal point right there. I'm not going to make the little things, but just to show you the pattern, be like move it once, move it twice, move it 3 times. So there's my first 0. And so I'm going to put a little arrow like that. All right, so all right. So that's how many. As you can see, it's a very, 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 very short amount of time. And the temperature here is 10 to the 32 degrees Celsius. So we have So insanely hot. This is the only time I'm going to write all this out for the presentations, just so you get an idea of what these numbers mean. And so the super fast inflation is going to continue. It's going to continue forever, basically. So at 10 to the negative 32 seconds, we call this the post-inflation period. So we're still less than a second, but the universe is basically a seething hot soup of electrons, quarks, and other particles. The temperature is so hot, though, it's still dark. There's no light shining. And the temperature here is 10 to the 27th degree Celsius. Now, keep in mind, we were just at 10 to the 32. Or 10, yeah, 10 to the 32. And so this is actually a massive decrease in temperature. This is a very rapid decrease because it's basically like if you had $100 and I took off 2 zeros, just like that, that's a big decrease in the amount of money you have. So I'm basically taking off 5 zeros here. 10 to the negative 6 seconds, still under a second. A rapidly cooling cosmos permits quarks to finally clump into the first protons and neutrons. We'll start seeing them begin the formation of atoms very soon. And the temperature here is still 10 to the 13th degrees Celsius, so it's still rapid cooling. And so the cosmos is cooling down. Matter has already won over dark matter at this point, and so the universe is starting to take shape, but it's still so hot that no light can shine. Now we're in about 3 minutes. You can argue anywhere from 3 seconds or so, 1 second to 3 second or 3 minutes. We see the formation of the first real atoms. So protons and neutrons come together to form nuclei of simple elements, but they're going to be unstable because it's still so hot. It's still so hot that the elements can't grab onto electrons. The electrons have so much energy that they are not bonding. They're not becoming part of the nuclei. So we don't have an electron shell, but we have nuclei. And we're going to see very simple elements: hydrogen, helium, some lithium, those first three on the periodic table. So these charged electrons and protons are what are preventing light from shining. Basically, the universe is a super hot fog. Sometimes this is known as the Dark Ages. Okay. Now, with the amount of change that we see very, very quickly in this first few minutes, I mean, we've dropped to 10 to the 9th degree Celsius. So you have that insanely big number versus this number. This almost seems manageable in comparison. But the universe is basically a super hot fog with no light. At about 300,000 years, there's a big change, big difference in time. The first atoms are finally formed. Well, the first stable atoms are finally formed. Electrons are able to be captured to make these stable elements. So most of the universe is hydrogen and helium, and that will actually continue through present day. Most of our universe is hydrogen. About 70%, 71% is hydrogen. And so light can finally begin to shine because the temperature has dropped and we have very stable elements. Skip to a few million years to about a billion years. Gravity is finally bringing this hydrogen and helium gas together to form giant clouds. These will form the first galaxies and the first stars. And so these galaxies are what we call proto-galaxies. They're the first galaxies to form. They're going to be very similar to another concept that we talk about when we talk about irregular galaxies. They didn't necessarily have perfect shapes or really intricate anything. But the first stars are going to start forming. Now, these are going to be very big stars for the most part, because there's a lot of hydrogen that they can work with. And the more hydrogen you have, the bigger the star can be. And so these stars are going to, live fast, die young, and those elements are going to be passed on to the next generation of stars. And so this is what's going to start making all those elements on the periodic table. Because as stars go supernova, elements are fused together, we get heavier and heavier elements. And so this is what's going to create that. Now notice the temperature change here. We're down to negative 200 degrees Celsius. Pretty good temperature change. No longer in the tens of thousands. So about 5 billion years after the Big Bang, just to remind you, this is all time after the Big Bang, something really interesting happens. A force known as dark energy begins speeding up the expansion of the universe. Now, in science, dark doesn't necessarily mean like you can't see it. It's dark or something like that. Really, in science, when we say dark whatever, it usually means I don't know. It means I don't know anything about this. It's literally just us saying, shrugging our shoulders and being like, It's like, I don't know what's going on. But what happened was it began speeding up the expansion of the universe. And what's interesting about this is that because it started speeding up the expansion of the universe, we said that the Big Bang happened 13.7 billion years ago. Okay, so if nothing can travel faster than the speed of light, then the universe should be, about 27.4 light years across. Like if it just expanded from a single point X here, it should be 27.4 billion light years across, right? But here's the thing. It's not. It is not 27.4. The universe right now, as we know it, is 93 billion light years across. Much, much bigger. Much, much bigger than what we should see. And we believe it's this dark energy that has actually caused the universe to start expanding faster than the speed of light at points. It also expanded faster than the speed of light during the superinflation, but it's continuing to expand. In fact, prior to this expansion, the universe actually, we believe it might have slowed down a little bit in its expansion. So we're still not sure what's going on, but that's something that scientists are working on. So 9 billion years after the Big Bang, we had the formation of our solar system. The sun is born and all the planets are formed. And we'll talk about the formation of stars a little bit later, but this is our star right there. Good old Sol. And about 13.7 billion years later, here we are. The ambient temperature of the universe is negative 270 degrees Celsius. And here we are. Now, some 20 billion years after the Big Bang, the sun is going to expand and turn into a red giant and burn our planet to a crisp. But, C'est la vie. Anyway, so after this 20 billion years, and so after everything happens, the universe, we believe, will end in a very cold and dark state. This is a theory called the Big Freeze, where basically all these elements, because matter can't be created or destroyed, it just changes forms, law of conservation of mass, but all these elements get used and changed into things that we can't form stars out of, and they get further and further apart and dissipate till basically all that's left are black holes, and eventually they too will fizzle out and the universe will end dark and cold. But that's a story for a different day. From a fiery beginning to a cold end, that's the timeline of the universe. Well, this has been Mr. Holsey for A Squared Sufficiently Understood Science. I hope you enjoyed the video. Please make sure to like, share, and subscribe, and hit the bell notification to know when we post a new video. All right, we'll catch you on the next one.